Hello everyone. Today I'll be introducing you to high-speed sintering. This is a polymer additive manufacturing process that blends inkjet printing and powder bed fusion. We'll look at how it works, why it was developed, and what makes it distinct from other similarly related techniques like selective layer sintering and multi-jet fusion. By the end of this presentation, you should understand not just the mechanics of high-speed sintering, but also its strengths, limitations, and where current research is taking it. At its core, high-speed sintering is a powder bed additive manufacturing process. Instead of using a laser like in selective layer sintering, it uses an inkjet printhead to deposit an infrared absorbing ink, and then an infrared lamp passes over to fuse those regions. It is sort of a cross between selective layer sintering and HP's multi-jet fusion, but it's mechanically simpler and faster than either method of 3D printing. Here's why I say it is a good way to think of it as a combination between multi-jet fusion and selective laser sintering. The main process components between both multi-jet fusion on top and selective layer sintering on the bottom are the same as in high-speed sintering. The difference with multi-jet fusion is that high-speed sintering uses only ink and does not use a binder and release agent. With the selective layer sintering process, the biggest technology difference is that the heat is applied in a more global manner and not a laser point. For some background on the process, high-speed sintering was invented by Professor Neil Hopkinson at Loughborough University in the early 2000s. He patented it in 2003, built the first prototype soon after, and by 2011, the first commercial machines were available. If you see selective absorption fusion being advertised by Stratasys, that's the same concept, just under a different name. Some of the big names in the world of high-speed sintering include Loughborough University, who currently owns the IP for high-speed sintering, Stratasys, who can do just about anything with regards to additive manufacturing, Voxeljet, who is a high-speed sintering machine maker, SAR, who specializes in printheads, and Fraunhofer Institutes, who specializes in manufacturing powder. An interesting thing here is that since Loughborough University still owns the IP, anybody who is going to be making a machine for this process is a licensee of the technology. The high-speed sintering process has 5 main steps: powder deposition, ink heating, layer advancement, and finally post-processing. We will walk through each of those now. We start by spreading a thin, even layer of polymer powder across the build plate, typically 300 to 1300 microns in diameter. Uniform spreading is important because variation in thickness can translate into uneven fusion later. Next, an inkjet printhead selectively deposits the radiation-absorbing ink onto the layer's cross-section. This printed pattern defines exactly which regions will fuse in the next step. The ink is usually carbon black based or another similar dye that easily absorbs infrared radiation and stays stable at elevated temperatures. The printheads are usually some form of piezoelectric inkjet technology. The particulates inside the ink are sometimes referred to as radiation-absorbing materials, or RAM in literature. You can see how this looks once it has been deposited, much like a 2D printer drawing each slice of the part. Because we're printing and heating instead of scanning, the system avoids all of the high-precision optic systems of selective layer sintering, which is where a lot of the time and cost come from in that process. Another thing to look at is the dots per inch between the multi-jet fusion and high-speed sintering processes. The dots per inch for a process like multi-jet fusion is typically much higher than high-speed sintering, but the limiting factor for print resolution is typically not print head DPI, but is actually powder particle size. Once the ink has been printed onto the top layer of powder, an infrared lamp sweeps across the bed. The printed, darker areas absorb more heat and sinter. The lighter, unprinted, and unsintered powder stays cool and loose. That unsintered powder conveniently supports the next layer, so no extra support structures are needed, like with the fused deposition modeling method. After a layer is fused, the build platform drops by 1 layer thickness, fresh powder is recoated, and the process repeats until the part is complete and ready to enter the cooling phase. This part of the process is very similar conceptually to other powder bed fusion methods. After printing, the build chamber cools gradually to avoid warping. This cooling time can be as low as 14 hours with a fast cooler, or as high as 48 hours without. Unfused powder is brushed or vacuumed away, and it can often be reused for future builds. Parts can then have any number of various other post-processing steps applied. The major subsystems for high-speed sintering are straightforward and are each closely related to the processes that were mentioned earlier. A powder hopper and recoater device, the print head, an infrared lamp, and finally, the heated build chamber. Now let's take a look at each component in a little bit more detail. The hopper holds the powder feedstock. A recoater blade or roller spreads it evenly onto the build plate. Some systems push fresh powder from a secondary piston to maintain consistent layer height, similar to the image shown. As I mentioned earlier, the print head is quite similar to those used in 2D printers and is often a piezoelectric type, but it has been specifically engineered to survive high build chamber temperatures. It rides on a carriage or gantry, distributing ink precisely where it is needed. Infrared lamps are usually quartz halogen bulbs. They can be fixed or moved synchronously with the print head. Their job is to deliver uniform, controllable heat without physically contacting the powder surface. The build chamber must maintain a carefully controlled temperature. Typically, it's slightly below the polymer's melting point. The main goal here is to straddle the line between the polymer's recrystallization temperature and its melting temperature. Preheating minimizes the energy the lamp must apply and prevents warping or delamination during cooling. This warping during cooling is apparent if the build chamber is not kept above the recrystallization temperature. If this happens, then the part is subject to warping due to recrystallization shrinkage. Common polymers for this process include PA12, the most commonly used nylon, PA11, which is a bio-based blend, or a blend of TPU for flexible parts. As I mentioned earlier, ink formulations use carbon black, graphite, or some other form of radiation-absorbing dye dispersed in a mixture of petroleum-based fluids. High-speed sintering only works with thermoplastics. Thermoplastics can melt, and the molecules in these chains can slide past each other and then re-solidify when they cool, locking them into place. While thermosets have cross-linked chains and can't be reprocessed once they've been cured. So materials like epoxies or phenolic resins are off the table for high-speed sintering. Typical layers are about 80 microns thick. Build temperatures for PA12 are usually between 160 to 180 degrees C. Print resolution is roughly 300 dots per inch, and build speeds can reach up to 6,500 centimeters cubed per hour, or approximately 1.7 gallons per hour, depending on geometry and machine size. High-speed sintering has some distinct advantages over the processes it is competing with. Because each layer is fused in a single pass, throughput is much higher than selective layer sintering and can be as much as 10 times higher. And while the processes are similar, high-speed sintering also beats multi-jet fusion in terms of volume printed per hour. Eliminating lasers and optics used in selective layer sintering also cuts equipment cost. And since the surrounding powder supports the part, there's no need for custom support structures, which simplifies post-processing requirements. Right now, high-speed sintering is limited to polymers that respond well to infrared heating, so the material library is smaller than that of selective layer sintering. Ink uniformity is critical. Uneven coverage can cause porosity or warping. Thermal control is also demanding. The entire chamber must stay within a few degrees between the recrystallization and melt temperatures mentioned earlier to maintain part integrity. The heart of consistent high-speed sintering printing is rooted in process control. The main parameters defining part quality are ink density, lamp intensity, powder properties, and chamber preheating temperature. Ink density dictates how much infrared energy the powder absorbs. Too little ink and heat absorption gives poor fusion where very little necking occurs. Too much causes over-sintering, resulting in surface finish problems. Unsurprisingly, the printing portion is not very simple, and a lot of work has gone into seeing how the density and properties of the ink affect the process. The influence of lamp intensity and chamber preheat is another area that lots of research has gone into to learn how to better reduce gradients and warping, and to better achieve bonded and repeatable parts. Another area of interest is in seeing how recycled powder influences the results of the process, and seeing what parameters need to be changed to maintain part quality. If any of those parameters drift from their target, then predictable defects start to show up. Low energy leads to porosity and weak parts. What is of interest in the image is that this is an example of how heat input can impact the porosity of a high-speed sintering part. In the study, PA12 was printed with two different lamps at the same power output, with the difference being the coating on the lamps, causing one of them to be a significantly higher intensity than the other one. The top, denser one was printed with a better reflective coating, leading to more heat input to the part. Unsurprisingly, the increased density of the parts printed with the lamp that had the better coating also leads to stronger and stiffer printed parts, as shown by the testing that was done on the printed parts. Here we can actually see the emitted intensity of the two 2 kilowatt lamps that were used for the tests in the previous slides, with lamp 2 significantly outperforming lamp 1, peaking at approximately twice the irradiance. Ink deposition is one of the critical parts of the process. Properties like viscosity and surface tension need to be carefully controlled. The viscosity changes with the amount of absorptive particles that have been added, and the surface tension determines how the ink spreads on the powder. A big part of the process is that the ink comes out in controlled drops and does not turn into multiple smaller drops. This can be predicted with the Onsorg number, which ties back to the Weber number, which ties back to the Reynolds number. The general rule of thumb is that this number needs to be kept between 0.1 and 1 for successful printing. So far, I've just touched on the main contributors to the process that can be tweaked to achieve better results. When you look further out at the rest of the process, there are significantly more knobs that can be tweaked to further improve the results and tighten up the irregularities. High-speed sintering has found use in lightweight automotive and aerospace interior parts, customized footwear, and flexible TPU seals or lattices. On the subject of footwear, Professor Hopkinson made the first individualized 3D printed soccer cleat, and since then, several Olympic athletes have competed in 3D printed footwear. That ability to print functional, flexible geometries quickly makes it appealing for prototyping and low-volume production. Looking ahead, there's strong interest in graded and multi-material sintering, where different inks or ink gradients are used to create a visual grayscale or to combine materials. In the top right is an example of the gradient used in one of my sources. Researchers are also working on better characterizing commercial printers and powders and temperatures for reducing and for quantifying their material properties. Increased utilization of the build volume is also an area that companies and researchers are looking into. The current packing density standard is around 12% of the build volume. Stratasys has been working to improve this and has been able to show packing densities of up to 23.5%. And finally, a key driver of this technology and research is sustainability. Improving powder recyclability and understanding how the process needs to be tweaked for increasing amounts of recycled powder is important to help speed up adoption of this technology. To wrap it up, high-speed sintering can be thought of as taking 2D printing concepts and applying them to 3D manufacturing. It's fast, scalable, and mechanically simpler than laser-based systems, though it is still maturing commercially. As materials, control methods, and sustainability improve, high-speed sintering could become a serious competitor for polymer part production. Thanks for your attention. I hope this gives you a clear sense of where high-speed sintering fits in the overall landscape of additive manufacturing, helping to bridge inkjet printing like multi-jet fusion and advanced powder bed fusion like selective layer sintering.